functions which differ of course by the homogeneous solution, and so they correspond to different kinds of boundary conditions that you want to impose. So, what we were doing at the end of the day was to just compute an integral of the following kind. So, we wanted to carry out this integration, and so we said we will first do the omega integration. So, we defined a few things, if you remember, omega of 3 vector k actually, which I will not indicate all the time. This is equal to square root of the positive square root of m square plus k dot k. So, what we did was to rewrite this. So, there is we were in arbitrary dimensions. At some point I will specialize to 3 plus 1 dimensions, but right now we can keep the formulae very general. So, what we have done is to use just partial fraction expansion and rewritten these terms. This is where we reached. So, there are 4 steps I guess to completing this integral. So, we have finished one, but let me state all 4 of them. The first step is to now carry out the so we would like to carry out the omega integration, but we will do that in 2 parts. One is to convert the omega integration to a contigration. This we had finished last lecture, but I will remind you of what our conclusions were. The next bit is to actually handle. So, what we see here is that there are 2 poles at plus omega k and minus omega k. So, we need to take care, and the contour here is omega contour goes from minus infinity to plus infinity along the real axis. So, these are real numbers. So, it is going to hit both of them, and I indicate that by a gap out here which we need to handle at some point in time. So, the integration is from minus infinity to plus infinity in the omega this thing, and what we have done is to write it think of omega as a complex number. So, what we mean by omega k here is the real part of that thing. Okay. So, we have 2 poles, one here at minus omega k, another at plus omega k. We need to handle that. Also, we need to close the contour, and I will just remind you later, but let us go through the process which we will go through, and we will complete this in this lecture. And so, next bit is to handle the poles at omega equal to plus or minus omega k. The third bit is to actually carry out, and maybe I should leave it as 1. The omega integral. Okay. Once we have done that thing, the next bit is to do the momentum integrals, which we will do in 2 parts. You go to do the angles, what I call the angular integrals. These are, and the last bit, which is do the mod k or the radial in K space. Okay. And in fact, in this problem all these steps can be carried out, and we actually we have discussed how to do this in last lecture. We by looking at e power I omega minus I omega of t minus t prime, and then we said we should write omega as some real part plus I times some imaginary part. Then this exponential will look like e power plus omega imaginary into t minus t prime and plus oscillating part, which you know exists. Okay. So, the idea was that we should close the contour. So, this is a semicircle of infinite radius, and so the point is that we want these contributions to go away, and we do that by looking for situations where this is exponentially suppressed. So, if you take t minus t prime less than 0, that means this is negative, then you can see that for large t minus t prime, or for that large omega I, this is vanishing, okay, in the upper half plane. So, the rule here is if t minus t prime is less than 0, you close in the upper half plane. So, the contribution of this goes away, and when you have the opposite thing, that is when t minus t prime is greater than 0, then you need omega I to be negative. Yes, okay, you can go ahead, or you could do things like you could choose, if you are unhappy with this kind of contour, you choose a square contour, and you worry. I mean, I leave it as an exercise for you to convince yourself that those things do not matter. Okay. So, once you can see, right, if you choose this kind of contour, if you convince yourself that it does not contribute, then just deforming the contour does not change the story. So, okay, but I am just sort of, this is intuitively the way to understand how it works, okay, but you can convince yourself that there is not any problems with what I am doing. Okay. So, this gives you a unique this thing. So, it says t minus t prime less than 0, close in the upper half plane, and if t minus t prime is greater than 0, close in the lower half plane. So, this is a nice rule which you can just quickly verify. There is no need to memorize the thing. Okay. So, this is what you get, and one point to remember is when you are closing in the lower half plane, the contour goes clockwise. So, it will give a minus sign when you do the residue of the pole. Okay. So, this is part 1. So, now we need to still handle the poles at omega equal to plus or minus omega k. This is a standard trick, which is to say that we either push this up here or down here into this plane, and or you do these things. So, there are 4 possibilities. Okay. So, this is part 1. Part 2 is shift into upper half plane or lower half plane. Okay. So, these are the 2 choices. You have 2 poles. So, there are 4 possibilities, which I will sort of indicate by this picture if you wish. Okay. So, the way to go about doing this is, suppose you wanted to, let us focus on this guy. This pole term is 1 by omega plus omega k. Suppose we wanted to move this to the upper half plane, we will use something called the I epsilon prescription, which corresponds to just adding an I epsilon this way, or this would be minus I epsilon. Okay. So, you just put it out here and say, so if you want to push it out here, so minus or plus I epsilon. Okay. So, let us look at the top sign, that would convert it to minus omega plus I epsilon, which means pushing it upward. So, this up first guy comes from the top sign, and similar thing happens out here. We just get 1 by minus or plus I epsilon. So, epsilon is taken to be infinitesimal and small. but and positive more importantly. Okay, I mean I should not switch signs on you. So, it is a positive number. So, you can see that there are 4 possible sign choices, and this is where our boundary conditions, the kind of things we want, become important. Okay. So, first thing is to look at what we will call the retarded green function. So, let me draw this picture of the I will need this. I look like I need everything. So, I have to give up something. So, let us draw another picture. So, again I will just draw it in one spatial dimension. So, this is t minus t prime. So, so the retarded green function should be 1, which should be, so g retarded should vanish here. Okay. So, it should, so something out here can only be affected by things in the past. So, in the future things it should not be affected. So, that is what we will call g retarded should vanish. So, let us see how we would go about doing that. So, g, so you can see out here in this in the future light cone t minus t prime is greater than 0. Yes. So, the thing is that so how the way to sort this out is to go back to what we wrote. So, we have phi at location x, which was equal to some integral over d 4 x prime g of x minus x prime and rho of x prime. Signs are not important factors, but this is, so this is the source, and this is the so we are getting the field at point x, and it should be determined by sources which are in the past and that is what I call the retarded guy. So, the retardation is taken into effect. This is what I call retarded. Okay. So, something in the past. So, so what I am saying, it is non-zero here. Okay. So, this is what we want. So, let us look for something which vanishes when t minus t prime is greater than 0. Yeah.
Everything will be non-zero when t minus t prime is greater than 0 and x minus x prime is greater than 0, right? Oh, sorry.
We will look at that. We will see. I mean, no, x minus x prime is not so important right now. It is only future or past. I mean, that is determined only by this. We will handle everything else. I mean, it has to vanish here as well, but that is a different story. Okay. Right now, we are just looking at where this should vanish in the past or the future light cone. Okay. So, coming back to this, so we want it to vanish when t minus t prime is greater than 0. So, what happens when t minus t prime is greater than 0? We close the contour in the lower half plane. So, if we do the following thing, if you push both of them into the upper half plane, then you will get there are no poles and the residue is 0. Okay. So, that is what it tells you. So, we see that for the retarded, so we push both poles into the upper half plane, and how does that work? You have to choose the negative sign out here. Okay. So, so that is equivalent to saying that, so you would write this thing. So, 1 by omega minus I epsilon minus omega k minus, so I will just keep track of these things, the exponentials are still there, okay, minus so this is the prescription. Okay. So, what about the opposite if you wanted? For G advanced, we just do the opposite, which is to push both poles. Okay. But intuitively you can see up to a sign, if you give me the retarded guy and the advanced guy, they will only differ if I just exchange the roles of x and x prime. So really I do not need to, I could do it by exchanging the roles of x and x prime, and then I can go to this. Okay. So let us choose g retarded and carry out the integral omega integration. Okay. And so now we need to carry out the omega integration. So clearly we have seen that g retarded of x minus x prime by our choices is 0 when t minus t prime is greater than 0. So we still need to work out what it is when t minus t prime is less than 0, and that is where we have to do the integral. Okay. So that is when we close in the upper half plane, and we have to take the residues of both of these guys. So let us go ahead and do this. So that what does let us remember the residue theorem. If you have something like this, f of x, some contour integral of some analytic thing, this should be equal to, if the contour is clockwise whatever, is 2 pi I times the residue, which is f of x naught. Okay. So let us see what is the analog of f of x here. It is e power minus I k dot x minus x prime times this 2 pi power 4 to omega k. Okay. So the residue will just tell you whatever is the value of omega, I replace that. So you will see that for this guy I would put omega equal to omega k, but for this guy I would put minus omega k. That is all I have to do. So if I do that, I can let us do that and write the answer out here. So we will carry out the so I am carrying out the integration, and but of course you will have the spatial integration, and remember that there is a 2 pi coming from here. So it will eat up one of the 2 pi cubed or whatever, but there will be an I. So 2 omega k, and the residue will give you an I, and then you will get e power. So first term will give us plus omega k. So let it give us. Okay, and the next term okay. So this sign flip comes because the residue is here, it is minus omega k. So this is what I get, there is a minus sign, and that is it. But life is good, there is an I out here, there is a 2 out here. So you can see that the time dependent part becomes a sine of omega k t. Okay. So this we can see becomes equal to, I think I made a mistake here. Oh, this I have been writing for 3 dimensions. So okay, times sine of omega k t minus t prime into e power omega k, which we can write out for once, okay. This is what we get. Okay. Clearly this space is not enough for what we have written. Okay. So we can put these two things together by as follows. Okay, I need to check. So this is the Heaviside theta function. So this should vanish when t minus t prime is less than 0. So I should change this. So theta, so the Heaviside theta function 0 for x less than 0, 1 for x greater than 0, and half for x equal to 0. Okay, step function or the this thing. Okay, so now you can see when t prime minus t is greater than 0, it is 1 and 0 for the other thing. And let us look at this and ask what happens when t equal to t prime. Okay. So we need not get into the semantics of what happens at theta, but you can see this sine function 0. So we can see that g retarded okay. So what does this imply? This implies, so what is the line t equal to t prime? This is this real line, this line. Okay. So any 2 points on this are space like separated. So what this tells you is that this green function vanishes on this line, on this line. Actually it is in the full space. So in other words, so the claim here is g retarded of x minus x prime is equal to 0 when when x minus x prime, x and x prime have a space like separation. Okay, we say that a separation is space like if this combination, that is t minus t prime square minus is less than 0, which is satisfied of course when t equal to t prime, which is 0, and this is okay. So this is, so here we are here I am making use of, so all I have shown is that it is vanishing on this line, or to be correct space like separated plane, hyperplane if you go to a higher the d dimensions, but I claim that any Lorentz transformation that you make can never take points from here to there, but it can take points here to anywhere here. Convince yourself, you pick a point here and work out what the Lorentz transformation is, which will take some point on this line down to here. There exists one. Okay. So in other words, it vanishes not just on this line, it vanishes in this whole region. Outside the light cone it vanishes. This is good news. This is something you wanted. Okay. So it vanishes not just here in g retarded, it does not vanish just here, it vanishes even in these regions. It is only non vanishing out here. So it is quite nice. Okay. So the claim is that g advanced is just the minus, you just exchange the roles. Okay. So so this is claim 1, which you can prove because it is easy to see. I only proved this for this sort of a thing for any and any x x prime, any pair x x prime. Okay. But the fact that this is a Lorentz scalar is what I am using, and the existence of a Lorentz transformation. So this is a simple claim, it is a fun exercise, do it only in 1 plus 1 dimensions, it is enough for you to see that, and then you can convince yourself that it holds always. Okay. And the next claim is that this is even easier, g advanced of x minus x prime equal to g retarded of x prime minus x. So I have exchanged okay. So this sort of completes what we wanted to do with respect to this, but we need to do a little bit more work, which is to carry out the k integration, that is that bit. But before we get into that, we can look at another possibility which comes about, which is there are two other possibilities, one up and one down. We could have done this, or the opposite, this one going down and this one going up. Okay. So, the way to understand those two possibilities is to, so the other two possibilities, so let us call it C and D, okay, and which I will write in a slightly different manner. Plus or minus I epsilon. Okay. Again, epsilon is some positive quantity. I leave it as an exercise for you to convince yourself that one of these signs does does this, what I have indicated here, and the other sign does this. Okay. But we will focus on the plus sign out here. This plus sign is something which appears in quantum field theory, okay, and it leads to something called the Feynman propagator. Okay. So, let us call C the plus sign. So, C is taking plus sign, and remember epsilon is positive. This so that gives you something which we will call GF, F for Feynman. Okay. So, you will see that both first thing to notice is that because there is always one pole in the upper half plane and one pole in the lower half plane, you find that when you do the omega integration, it does not vanish in either one of them. Okay. So, it does not vanish here, nor does it vanish here. Okay. So, it is non vanishing out here, but even more interesting is the fact that it actually does not vanish even in space like separation. Okay. And that I will leave it as an exercise, but I will indicate to you how it goes. Okay. So, this object actually GF of x minus x prime up to some multiplicative factor in quantum field theory is the time ordered product of two fields x, phi of x prime. Okay. So, this is called the Feynman propagator. Okay. And so, this also appears in will definitely appear in the next course. So, time ordering here is just that you want to put so time ordering is that you might have seen this in quantum mechanics. You need to put so you order these things such that the one which is of earlier time should be to the right, and the one later comes to this thing. So, that depends on whether t minus t prime is greater than 0 or less than 0. Okay. So, now what we will do in the next 15-20 minutes is to complete the carrying out the integrations. Okay. So, we have only done the omega integration. We need to do the so the third part is to carry out the A bit is to actually carry out what I call the angular integrations. It will become clear why I am calling them angular integrals. Coming back to after we carry out the omega integration, so we have an integral which looks something like this d. So, let us put d equal to 3 because I can be very explicit with regard to the angles. Okay. You can generalize to any dimension. So, you have d cubed k here divided by 2 pi cubed some sine omega k of t minus t prime e power I k vector dot x minus x prime divided by square root of okay. So, this is the integral we need to carry out, but there is something very nice going on out here. This is only a function of the magnitude of k. Okay. So, is this omega k, this also the same thing, and so the only dependence on any on k, the other parts of this thing would come through this sort of a thing, and it is a standard way of there is a standard method of doing this. You, since you are averaging over all k, you can, and this is for a fixed x minus x prime, with no loss of generality you can say that x minus x prime is along z direction. So, with no loss of generality, yeah, there is a theta here, but I am at this point only focusing on the integration part of this thing, okay, with no loss of generality. Choose minus x prime to be z minus some z prime along the z direction, okay. And to even more simplify things, I will just set z prime to be 0 because it is only on the difference, okay. Also choose okay. Then this object actually can be written, if you wish. Actually I do not even need to do this, let me just okay, let us since I have made this statement, let me use it. So, what we see here is now k, this would just become the exponential. So, k dot x minus x prime is k z z after I do these two things, but k z can be written as magnitude of k, okay, times cosine theta into z, okay. At the end of the day what I will do is mod z will become mod of z minus mod of r minus r prime, okay, at the end. So, this to recover the whole thing at the end set z to okay. So, this is the angular part in k space, you can see that I need to do the cosine theta integral, it is independent of phi. So, d cubed k can be written as d of mod k, which I will write as dk. Please do not confuse this with the 4 vector k out here, this is 4 vector square, but this is the magnitude of the 3 vector k, okay, just for, otherwise I have got to keep putting mod of k, k square d phi d cos theta, okay. I prefer to write it as d cos theta because it is just sin theta d theta, and but cos theta goes from -1 to +1, okay. So, instead of making one more step where I change variables, you can see it depends only on the combination cos theta, which runs from -1 to +1. So, now it is very easy to do the cos theta integration. The phi integration is the easiest, it is independent of phi, that will give you a 2 pi, and I need to do this guy. So, let me write that out and do this, do the integration. Okay. So, let us just call this quantity I, and so that leaves me with, so I get I equal to I forgot a sign. Okay. So, I just need to do this, but this is very easy, and so in fact I will, let me do one thing, I just call that combination R instead of calling it Z. So, this just gives me e power I k r divided by cos theta evaluated between -1 and +1. Okay. and now the k integration goes from 0 to infinity. Okay. So, what does this give you? It gives you e power I k r minus e power minus I k r, because cosine theta is plus 1. So, this is equal to there was a 2 pi cubed, right. So, now that becomes 2 pi square. Okay. So, we get two terms, and but the k integration goes from 0 to infinity, but let us ask what happens to if I go ahead and take k to minus k on this term, then the exponential k becomes e power I k r. It looks exactly like this. This k goes to minus k, so this becomes a plus sign. Okay. And what happens to the limits? The limits become 0 to infinity, 0 to minus infinity. Yeah. So, yeah. So, let me write this out as two terms. They should not cancel if I. Okay. So, the first term is just integral 0 to infinity. So, this, yes, I am okay, I am okay. So, yeah, let me just say it in words. So, what happens is that this term, so this becomes if I take k to minus k out here, this becomes e power plus I k r, which is similar to this. This becomes minus k r, this flips sign out here, but let us come back to this this guy, it is odd. So, this will also change sign. So, that will convert an integration from 0 to minus infinity to flip it and make it minus infinity to 0. So, you can see that I can rewrite this term by putting it back into this with by changing the limits to go from minus infinity to plus infinity. Okay. Now, you can see dimensionality matters. Okay. Okay. So, now we are only left to do one dimensional integral. Okay. So, we have finished the angular integrals, and you can see in other dimensions there might be more angular integrals, but they will give you some constant functions, just like we got the phi integration gave you a 2 pi or whatever. So, you need to be a little bit more careful about how the angles work out, and so I leave it as an exercise for you to do it. But there is a nice article by Professor Balakrishnan in this nice journal called Resonance. There are two articles by him. I think it is titled something like wave propagation in arbitrary dimensions or something. Okay, I will put up the exact reference on the course web page, and it is a two part thing, and there is something about 3 is the best. So, he actually discusses things in more arbitrary dimensions. I do not want to do that, okay, because I just want to work out one example. But so, it is a two part series, which is a fun series of articles. But now, coming back to this, this integral can be done, and the answer, okay. So, the last, which is the fourth part, the k integration can be carried out, and the answer can be written in terms of Bessel functions. Okay. So, the way to go about understanding this is I have already given you the hint. I have told you this can be done written in terms of Bessel functions, and so you need to know an integral representation of the Bessel function. Now, you are not expected to remember this, but there is this wonderful books on special functions, one of which is Abramowitz and Stegun. In fact, the people at I guess NIST or whatever they have actually put this online now, and it is updated. So, you go, I mean, you just search for this. In fact, I think there is even a Wikipedia entry for this, and you can get look for Bessel functions out there, look for integral representations, and you will have to play with it a bit. It is not like every integral that you see here it should be there in Abramowitz and Stegun. You may have to massage it a bit, but I think I have given you enough of a hint that it can be written in terms of Bessel functions. Okay. So, yeah, so that is so you can indeed complete this. Okay. So, coming back to the Feynman propagator, okay. So, what you will see in the Feynman propagator is that you will get similar integrations, but we are interested in what happens. So, we want to analyze what happens for space like separations. Okay. Out here, of course, if you put t equal to t prime, things vanish, but there what you will see that only one here the way we got sign of omega k t was that both of the poles contributed. So, it is very easy to see that what you will end up getting is not a sign, but one of the exponentials only. Okay. And unlike here where everything was real, that is pure imaginary. Okay. So, that is also important to note, and so you get an exponential. So, the key point is if I put t equal to t prime, that will not vanish. So, you are left to do an integral which looks like this. So, the integral has this form. Since I am not actually going to work out all the various factors, I will drop various things and only write out the k dependent pieces. This is not there. I get these only these 3 pieces. This is what I get. Okay. So, I need to do this integration, but again this can be written in terms of Bessel functions, but what we are interested in asking is what happens when the separation is large. So, what happens okay, and I will just write out the answer which you can actually see from dimensional grounds out here. So, so yeah, what do we get? So what you will find is that you will I will explain to you why I am saying that it comes from dimensional grounds, okay, or maybe you could do saddle point or whatever. So, you look out here and you can see that the dominant contribution is coming when k square equal to m square. Now, you think of k as a complex number, but you can do it from writing out the Bessel function and asking what happens. So, you get I think k1 of mr is what you get the final answer. This is a Bessel function which for large r has this e power minus mr behavior. Okay. But what I am showing you is that actually you could do it without even looking at these things. So, dimensionally this dk and this dk goes off. So, there is a k square going around. You compensate for that by putting an r square. There is a kr out here, wherever you see a k you put a mr. m is this correct? I think it should be power half, yeah. Okay. So, I just put these things, but the key point here is that it is exponentially suppressed. Okay. So, it does not vanish. The point I want you to take away from here is that the Feynman propagator does not vanish, okay. But this is something happening in quantum field theory. This is not something unusual. I mean, we know that there can be classically forbidden regions in quantum mechanics. Suppose you have a wall, a potential of this kind, and you have energy. So, this is V of x versus x. So, if you choose the one dimensional particle with energy which is less than that of the barrier, you know that if you look at the wave function, the wave function is not 0 out here, it is exponentially suppressed. Okay. It is similar to that. Okay. So, what you thought classically was 0, quantum mechanically, I mean there is a reflection, it has, I mean it has some non-zero answer, but nevertheless that is small in some sense, okay, in as much as h bar is small. So, in that sense, so this is so it shouldn't, it is not like meant to be a shock or anything that it happens in quantum field theory. We have seen it already in quantum mechanics in some sense, and so but it is pleasing to see that it actually dies off very, very fast. Okay. You may ask what happens for massless particles. I think I will leave that for you to think about a little later. Okay. But for now I think I will stop here, and so I think there are all these exercises. I would strongly recommend that you should carry out this last integration. Okay. I did not want to bore you people with discussing special functions, but I think we should be at a level where we think of the Bessel function should be on par with the sine and the cosine functions. So, when you are in high school, sine functions and cosine functions are nice functions, you know everything about it. Okay. But if you take things like Bessel functions, now we are at a level where you should think of them on par. Of course, there are properties of the Bessel function which are not that obvious as that of the sine function. So, when does the sine function vanish? Whenever its argument is 2 is some n pi, you know that. But if you want the same story with the zeros of the Bessel function, that is not, I mean you need to look at the tables. Again, these books are fantastic. You want to know what is the first 0 of J1 or whatever, you can see it out here. But there are certain properties which you should be aware of, the fact that how it goes to its behavior near 0 argument and its behavior at large. So, large things, the j's become oscillatory while the k's have exponential, it could be. Okay. So, these are things which you should know and become familiar with. If you are not, it is okay, but there is a chance for you to play with these things. In principle we will not be using a lot of it in this course, but I think we have to move to the next level where we think of Bessel function as something normal. Okay. Thank you.